Hello, everyone. Today you'll get a flavor of quantum entanglement by looking at probabilities of various states. We will go back to talking about coins, both classical and quantum. Let's start with a classical coin, like the one you might have in your pocket right now. A coin has a head side and a tail side. We will assume that our coin is fair, so the probability of obtaining heads is equal to that of obtaining tails, which is 1/2. We will deal with a situation where we toss the coin several times. We call each time we toss it a trial. These trials are assumed to be identical, independent, and have two possible outcomes. Note that we consider the experiment in which a single coin is tossed n times the same as one in which n coins are tossed once in terms of distribution of outcomes. The probability distribution of the outcomes is given in this case by the binomial distribution. So if we let P be the probability of success, Q be the probability of failure, N the number of trials, and X the number of successes, then the binomial distribution is given by this, where N choose X equals N factorial divided by the product of X factorial and N minus X factorial. What do we mean by success and what do we mean by failure? Well, we get to decide at the beginning, so we can say that obtaining heads is a success and obtaining tails is a failure, and vice versa. Now, let's look at the situation where we have two fair coins. And when we say that the outcome corresponds to a success, we will mean it's obtaining tails. Here, P equals 1/2, Q equals 1/2, N equals 2, and the binomial distribution is reduced to this. X equals 0 corresponding to no tails outcomes in either coin, and the probability in this case is 1/4. X equals 1 corresponds to getting heads for one coin and tails for the other, and the probability of that is 1/2. And finally, the probability of obtaining two tails is 1/4. Now, let's switch to quantum coins. Here we have Queen Entanglia on the head side of the coin and the cat on the tail side. We will assume that the quantum state cat psi is in an equal superposition of both sides. So we have a fair quantum coin. To mimic the classical situation on the previous slide, we will bring a second identical quantum coin represented by cat phi. So we have two quantum coins now. Let's take the tensor product of the two coins to obtain this. Remember that the absolute value squared of the coefficient of each ket corresponds to the probability of obtaining that ket upon measurement. Well, this implies that the probability of obtaining two heads is 1/4, of obtaining one head and one tail, which coin is heads and which tails doesn't matter, is 1/2, and the probability of obtaining two tails is 1/4. Well, that's the binomial distribution for n equals 2, identical to the analogous classical case. One thing I want to point out is that the total state of the two quantum coins, or two qubits, can be written as a tensor product of the state pertaining to one of the coins and the state pertaining to the other coin. That is called a separable state, which is the opposite of an entangled state. The latter is a state that cannot be written as a product of the state of coin number 1 and the state of coin number 2. An example of an entangled state is this: a linear combination of obtaining two heads and two tails. The trials in this case are no longer independent. Therefore, the probability distribution of the outcomes is no longer binomial. Before I leave, I have an exercise for you. Calculate the probabilities of outcomes for 3 fair classical coins, then 3 fair separable quantum coins, and compare the results. See you soon!